This is help with number 10 on worksheet number 1 for separable differential equations. And in number 10, you are given the differential equation that the change in capital T over change in baby t. And I'm going to tell you that the reason we're using t's on this one, even though they're awkward, is because this is actually Newton's law of cooling model. And this is standing for change in temperature. And this is standing for over time. So when you take something and you put it in what we call a surrounding medium and it starts to cool, we can chart the rate at which it's cooling by simply saying, well, how hot is it right now? And then we'll wait a couple hours and we'll see how hot it is next. And then we chart that rate of cooling. And Newton's law of cooling says that the rate at which the object cools is directly proportional to the difference between the temperature and the temperature of what we call the surrounding medium. So what that means in this case is that the surrounding medium, like for me right now, if I were to die in this room, that would have been a 70-degree room. My current temperature is 98.6 degrees because that's my body temp. And the rate at which my body cools can follow this model. What that allows me to do is predict the temperature at any given time. So you'll notice that on the number 10 there's a negative here, and if usually when you see Newton's law of cooling, which we're going to study a lot more in another section, so don't worry if you don't understand the science behind it, that'll come later. We really just need to know how to separate this and get a model that'll give us our temperature at any given time. But that K can be either a positive K or a negative K, and usually you see it written as just K, and then when you solve you get a negative for it, where in this case, since it's a negative K out there, I solve and I get a positive. But for this problem, I can't even figure out what K is. Here's why. They only give me one piece of data. And they tell me that the temperature at time 0 is 140 degrees. So what that means is maybe I took a pizza out of the oven and it was at 140 degrees and I set it down on the counter, and the counter, the room temp was 70 degrees, and that pizza starts to cool. And I'm going to get and it cools fast at first, and then as it approaches its surrounding medium, that cooling slows down. So I am going to figure out how I can get a model for the temperature at any given time. So first thing I'm going to do is separate. Just a second here. I forgot my d big T is equal to negative k and d little t. And negative k in this scenario represents a constant. We don't know what it is. So now after I separate, I'm going to integrate. On the left, I have the natural log model. Basically, if that's u, du is 1. I have u prime over u, which is the natural log of u. Technically, it's absolute value, but this started at 140 degrees and it's going to cool, and it can't go below 70 degrees because that represents the temperature of the surrounding medium, either the water it was put in or the room that it's in, or, it depends on the situation. So I'm able to leave those absolute value bars off. On the right hand side, I'm going to get a negative k times baby t, because k is some constant that I don't know. But then I also have plus big Carl. So I have two unknown constants, which really requires 2 points, and I'm only given 1. So my answer is still going to have a variable in it, and that's why I'm doing this one for you. So my goal is to solve for, I dropped my pen, solve for capital T, and it is stuck inside of a natural log. So I am going to exponentiate both sides. On the left, e to the ln of stuff is just the stuff, because e and ln are inverse operations. On the right, I'm going to rewrite that like we've been doing in class as e to the kt times e to the c. Because when we multiply, we add exponents. And conversely, when we're adding exponents to the same base, we can break it into a multiplication problem. The reason we do that is because then we can attack this and we can just call it some other constant. And so we're going to call that some other big constant. And I'm going to just call that C for this case. So that's just going to be some other constant times e to the negative kt. So really what I have is my capital T is going to have to equal, I'm going to add 70 to both sides, 70 plus C e to the negative k times, and this I'm really got to be careful with my t's, that's a baby t. My next thing is to figure out what is this, and they did give me an initial point. They said at time 0, the temperature was 140. So what they're giving me is T, big T. So what I know is I'm going to indent 140 is 70 plus, I don't know, e to the negative k times 0. And e to the 0 is just 1. So 140 has to be equal to 70 plus c. So that gives me a 70 for my big C. So back outdenting to my equation for capital T. It's going to equal 70 plus 70 e to the negative k t. And that's the best I can do right now. In order to find, and that's the answer that's going to be on your packet, in order for me to find this, I would have to be given one more point on the curve. So now I'm going to have you kind of understand the significance of this. If I were given one other, if I knew that when I took something out of the oven it was at 140 degrees, and then an hour later maybe it had cooled down to, I don't know, 100 degrees, right? This would help me find C, this would help me find K, and when I'm done, I'd have a model for the temperature at any given time. Now, again, if this were a forensics problem, and I knew that the rate that body temperature was cooling over time is directly proportional to the difference between the temperature of the body and the surrounding medium. So suppose someone was discovered in a hotel room dead, and we know that the temperature was set at 72 degrees. That would go right here. And I would say, okay, right now we walked in and the body was 82 degrees because we had been there. We got there and he is already dead. And then let's even say a half an hour later, the body had cooled to 80 degrees. What we could do is figure out time of death from this, because we would solve for the body temperature by doing this whole process. This would help us get big C. This would help us get little k. And again, I'm talking ahead of myself, but you can kind of see the significance. And then I can figure out the time of death by replacing this with a 98.6 degrees, because I would want to figure out, well, when was the body 98.6 degrees, basically meaning when did the death happen. So kind of applicable, and that's what's coming, but the separation process is what you need to know, and that's it for that one. Have a good one. Peace out, Girl Scout.